my name is Alejandro, and welcome back for day 52 of me doing the NeetCode 150 challenge. So today we're doing another medium linked list problem, and without further ado, let's get straight into it. Okay, today we get a LeetCode medium, problem 19, remove nth node from end of list. Ooh, I see we have an attempted here. So does that mean I've never solved this problem before? I see I've only had wrong answers. This was November 10th, 2022, so this was more than 2 years ago. That's actually, so in terms of years, yeah, 3 years ago, because now it's 2025, but 2022, November 10th, so over 2 years ago. Okay, so let's see if we can solve it this time. It'll be a good refresher. So let's do this. Given the head of a linked list, remove the nth node from the end of the list and return its head. So, okay. Well, I see. Okay, this is actually not too difficult. You'll have to traverse the list at least once, just so you can know, okay, which one is the nth node, right? Sorry, forgive me that. Once you do so you have really two options, right? Either you can store everything in memory so that, like, you only do one iteration of the linked list, or you do one iteration of the linked list to get the count, and once you get the count, you do another iteration until you get to, the count minus nth node, and then make that, backwards, and then do the head, right? So we can do a O of n memory, but technically only one iteration in the of the linked list, so O of n time and O of n memory, and we can do this in O of n time, O of 1 memory, but O of n being like, two iterations of the for loop. So follow up, can you do this in one pass? Okay. Oh. Well, yes, with more memory, right? The point is you do this in one pass, and then you store everything in. Okay. So I have two ways to do this. Essentially, it's like, okay, what we can do is just say, hey, we can have a dictionary here, right? We'll have a dictionary, and we'll have an index is equal to 0 at the beginning, right? And then we'll say cur is equal to head, and we'll say while cur. Loop invariance will be cur is equal to cur.next, and here we'll say, hey, d of index is equal to head cur, and here we'll say, hey, index plus or equal to 1, right? Surely. And so here, so index will be 0 if there's no elements. For every element we do, we have index plus 1, right? So here we're going to print index, but this is essentially the count, right? So here we'll just return head. We've done nothing, so this will be an incorrect solution, right? But here we're printing out 5, where there's 5 elements, so this is very good. This is very, very good. And in fact, here we can print our dictionary. Is n always guaranteed to be a valid number? SZ. Number of nodes in the list is SZ. This is between 1 and 30. And n is always less than or equal to SZ, and at least 1. Okay, so this is good. So we are using a lot of memory here. That is very true. But yeah, so essentially, the node I want to remove is after index 3, right? So if I do 5 minus 2, that gives me 3. So I can go to, so I want to do node is equal to d of index minus 1 minus n. Node.next is equal to d of index minus 1 minus n, not plus 1, but plus 2. And then return head. And then this would give us a correct solution. Unless this does not work. So let's look at this example. So yes. Count equals index. If count is so the length of the linked list is at least 1. If index equals 1, only one node in linked list, so return none. If index is equal to 1, then we'll say assert that n is equal to 1, and then return none. Right? So we can just do that. A simple if statement check there. we still don't have things like this. So here we might just do none. Right? So here we might do d.get this and none as default. Right, so this seems to work. Let's comment out these print statements and let's just submit this and see if this works. It does not. Okay. So let's see the case we failed. We have two elements and n is equal to 2. So when n, okay, so when n when n is equal to, okay, here we'll do if index is equal to n, return head.next, right? Because we have at least one element inside of the head, right? Yeah, there's at least one node, so we can always do head.next. Okay, so we can get rid of this, and now submit. And there we go. Okay, so 6.79%, but because we're at 3 ms, there we go, bada bing, bada boom. So this might be a little slow to do this with a dictionary, but technically we only needed to do one pass of the linked list, right? So that's actually pretty good. And here we can actually do this as index plus 1 minus n. Right. There we go. If I do this, this is incredible. Like I get to a situation like this, right? Yeah, so here I'm going into an infinite solution. There we go. So, oh yeah, memory limit exceeded. There we go. Okay, so now we're at 0 ms, beats 100%, bada bing, bada boom, very nice. Okay, and so we did this with just a singular pass, which is what the for loop wanted us to do, right? The other way that you could do this, essentially, is you could just do one full pass of the linked list, and then, you know, get the count of the linked list, so you get how long the linked list is. And once you have the length of the linked list, you know which index you would need to delete from. So then you retraverse the linked list until you reach that index, and then essentially, you know, perform a delete operation right over there, bada bing, bada boom, and there you go. What I did instead is I essentially said, hey, let's keep track of a dictionary, so that way we essentially can map each node to, like, you know, the index as if though it's like an arrayable, an indexable linked list, and then it's like once I have that information, then we can go like, aha. Since I know where in the linked list I want to delete something, I can now look up that position in O(1) time instead of retraversing the linked list to get back to that position. So as always, in all my videos, I do a quick recap of how I was able to solve the problem. So for this one, essentially, again, there are two ways to solve this problem. One way is by doing it with 2 passes and O(1) memory, and one way is to do it with 1 pass and O(n) memory. Since the follow-up asked if we could do it in 1 pass, I chose to do the 1 pass solution, right? And so the way that I did this is essentially I kept track of a dictionary where I'm going to keep track as the keys being the nodes inside of the linked list. So in Python, an object class, like for example this class list node, are always hashable, and so you can essentially use them in a hash map, which is very, very convenient. You're able to hash an object or instance of a class in Python, so it's very, very helpful to use a hash map for these kinds of cases. And so essentially, like, one thing you definitely have to do is you have to know how long the linked list is, right? If you want to return the nth node from the end of the list, you must definitely, you know, at least know how long the linked list is, so you know which node is the one that is the nth node away from the linked list, and then from there figure out, like, okay, this is the node that I want to remove, right? And so essentially what I did is like, okay, let's keep track of an index where we're going to assign each node to essentially an index, right? So this one is going to be the one on index 0, index 1, index 2, index 3, and index 4, right? So I have a variable here that I initialize to be the head, and I essentially traverse the entire linked list, right? While cur, i.e. while it is not none, i.e. we haven't reached the end of the linked list, then we're going to say, hey, the dictionary at with key of this index, oh, by the way, we're not hashing the objects, we're actually hashing a number, but if you did need to hash the objects, you can, right? So there you go. But here we say, okay, it's like for example, the first node will be at index 0, right? And then we increment index, so that way when we go into the while loop again, then like, you know, index will be 1, and so the next node will give it index 1, and this one will be index 2, and this one will be index 3, index 4, right? We initialize it at index 0, and there we go, and so then plus 1, and then create equals square.next until we exhaust the entire linked list, right? Now we notice that like index at the beginning is 0, as if though we've seen 0 elements, right? Every time we see an element, i.e. cur is not none, we append that element and increment index. So essentially index at the very end is going to be equal to the number of elements we have in total, right? After this while loop, for example, in this example, we'll have index equal to 5, right? It'll be a 0, then it'll become 1 after we made this the index 0, we make this an index 1, so now index plus or equal 1 is equal to 2, we make this index 2, index 3, we make this index 4, then, you know, plus or equal to 1, so our index value is now 5, but then when we get the end of the linked list, we terminate out of this while loop, and so index equals 5, which happens to be the length of the list, right? And then we have to think, right? For example, here, n is equal to 2, and so we want to delete 4, right? And so the point is that, like, okay, if I take the length of the linked list, and I go minus 1, minus 2 here, I'm essentially at this node over here, right? So like, you know, this is index 4, my current index value is 5, so it's like, you know, 5 minus 1 would give me this index 4, minus 1 would give me this index 3 here with value 4, and so essentially if I subtract index and n, I essentially get the index of the node that we want to delete. But now, how do we delete a node? Essentially, I need to look at the previous node and make this guy's next not point to this node, but essentially point to this node over here. So I have to do not just index minus n, but index minus n minus 1. So that I can get the node that comes right beforehand and essentially make that next node the one that came after this one that we want to delete, right? So I do index minus n as well as minus 1. So that node that comes previously, I can make that node's next value no longer equal to this node. So I index minus 1 minus n, the next node will be plus 1, but then we want the one that's right after that, so we do plus 2, right? This is the index, the node at that index, minus 1 and plus 2 just becomes plus 1, which is why I have index plus 1 minus n, right? And then it's just like, okay, if we're like at the end of the linked list, then it's like, okay, just do none by default because that's what we want to delete, right? Like for example, if the one we want to delete is 5, and we were at the previous one, there is no node over here. So what do? We say, okay, the node over here, there is no node, this is just none, so essentially the next node after this will just become none, right? So we just make that to handle that base case. Another base case is like, okay, what if there's 5 nodes in here and we want to delete the fifth node from the bottom? So i.e. we could go here, there's no node previous to that, so our algorithm will work. So we just recognize like, okay, if our index, i.e. our count of number of elements is equal to the n, then it's like, okay, that means we want to delete the first node, which means we really want to return the linked list from here. So essentially if this is the head, we delete this one, so we return head.next to get the rest, right? So if index is equal to n, we just return head.next, bada bing, bada boom, right? So if it's not, then we go in here and, you know, get the node that we want to delete, which is the index minus n, go 1 before that, and then delete the next node, right? If it happens to be that we're deleting the very last node, then this d.get index plus 1 minus n will not be a thing, so we just default to none because again, that's what we want the rest of the linked list to be. Like if we're deleting this 5, we want the next node after 4 to just be null or none, right? Instead of this 5, and that's pretty much it. And then once you've deleted the node that you want to delete, then you just return head, right? But the trick lies in using a dictionary so that when you traverse the linked list, essentially you keep track of the node at every position, and that way you know which position you want to delete a node at, and using that you can do an O of 1 time to get the node that you want to delete from, and then, you know, delete that node all in O of 1 time. There you go, bada bing, bada boom. If you wanted to do this with O of 1 memory, you could. You just have to use, you know, a count variable to count the number of elements in the linked list, subtract that by n, subtract that by 1, and then, you know, retraverse the linked list. And then once you get to that position, essentially be like, okay, my current node's next node is now going to be equal to the one that was after that, right? So essentially you do this, but you'd retraverse the linked list again, and you could do it in O of 1 memory. But again, since the follow-up said, can you do this in one pass? I chose to do it in the one pass way, and we got, you know, 0 ms beats 100%, so there you go, bada bing, bada boom. Very nice and efficient solution. So hopefully that solution made sense, and yeah, so that's pretty much it for this video. Let's make sure that we keep track of the fact that we did this problem. So there we go, nice and crisp, and yeah, so that's pretty much it for this video. If you did find it useful or enjoyable in any way, shape, or form, I would highly appreciate if you left a like or a comment. But otherwise, I'll catch you in the next one. So until then, ciao, ciao, my friend. Bye-bye.